So just to recap, the library, I'm going to just run the R and then load the wage pan data. I think it is taking a bit of time. Yeah, it has loaded. And I'm just going to run quite a number of them, quickly jump most of them. There are some few things that I will not have to do all, because I just want to, these tests that we are about to study are tests that are done after the running of the modules. And because we are going to create a model, a table in the end, it requires that we have all of these other things. So that is why I'm trying to run all of this. So that's the POLS New West, fixed effects, the LSDV, fixed effects with 2 ways, with time, with that, and then we have the New West fixed effects. We have the random effects. We have this. We run multiple tests. Now we are left with the test. So let me go back to the slides. So here we are. Can we apply POLS to our data, or we cannot apply POLS to our data? That's a question. And to do that, we do some test called pullability test. In other words, do you think the POLS that we had is a good one? And this test is a child test for a coefficient. Okay, it tests that the null hypothesis is that the same coefficient apply to each individual. So the data is pullable. That's a null hypothesis. The data is pullable. In other words, it's all right to use POLS. And the alternative says that it's not all right to use POLS. And in this test, if the p-value is less than 5%, we reject the null hypothesis of POLS and conclude that POLS cannot be used. And so we have to go and use a variable coefficient model. So let's go to see, let's go and see the R. Please confirm if you can see the R.
I can't, Doc. I can't.
Okay. So this command number 626 is an R code for the test. Watch it. I'm calling it pull test. Okay. So we want to check. When you can see that I've used small number of independent variables, because for this very data set, the small number of independent variables that you use makes the test workable. So I'm going to run this test. Okay. That is running on the right here, and this is a test. You can see that the p-value is almost 0.52, so it's almost 5.2%. Okay. Now, this test is, so if you go by this test, okay, the p-value is about 5%. And normally, if the p-value is less than 5%, it means that the thing is not, POLS is not good. It means that we cannot use POLS. Now, the one we are having is 5.2%, which means that we can use POLS for this very one. Okay. Another test, another way of running the test is by comparing the POLS with the fixed effects. That's another way, just to check whether pulling is possible. Okay. Whether pulling is possible. So we run this as well. Let's look at the results. You can see that this one is significant. Okay. Now, let me tell you something. This first one that I did, do you realize that I used small number of independent variables? Do you see that?
Yes.
Yeah. But then when you look at the POLS, the W POLS itself, this one, okay, the number of independent variables was everything. That's what you can see here. So if you check it here, it was all the independent variables that I ran in the original model. In the original model.
Yes.
So you can see that that is the one, the command number 627, that's the one that you have to use to make your judgment. So what does that one say? And when you look at the p-value, that one says that the p-value is 0, which means that we can reject the pooled OLS. And so it means that we don't have to use pooled OLS for this. What I was doing is I was just comparing the pooled OLS with the fixed effect model. The fixed effect model is this one. You can do different kinds of fixed effect model. You can even use other things. So I've written here, you can do fixed effect two-way. You can use first difference, okay? And then you can use least squares dummy variable. Any one of them, you can compare it with a pooled OLS. I decided to just compare it with a fixed effect. And you can see that it says here that we cannot use the pooled OLS. Why? Because you look at the p-value, that's it. And you can see that the alternative hypothesis is instability. The null hypothesis will always be the stability. In other words, pooled OLS is stable, but the alternative is instability. So this test actually indicates that pooled OLS is not going to help. Let's move on. But it doesn't mean that because of that, you will not show the pooled OLS result. The next test is you can test for the individual and time effect. In other words, you can test the null hypothesis that the fixed effect makes no difference. The fixed effect doesn't have any difference. So variables that are fixed, they don't actually do anything for the data set. The alternative would mean that they make a difference. So basically, you are testing for individual specific effects, whether they are good, or time-specific effects, whether they are good. Okay. If you are doing for time, then you are saying that time effect makes no difference. But if it is individual, it means that individual effects make no difference. This is a Lagrange multiplier test. And it's also based on the result of the pooled OLS. So we can run that. So I'm going to show that here in the R. So this is a way to run that test here. So this is our pooled OLS as we know it already. But watch it. This pooled OLS that I did, if you check, let me just go a bit. If you check this pooled OLS carefully, you will see that under model, it is pooling because it is the same pooled OLS that we did before. That's all you're doing. So that's the normal pooled OLS. We've run it. This was a result we had before, if you can remember. Now, let's do the comparison of the pooled OLS with the time, the two-way time effect. So we are doing both individual and time. We want to check whether individual specific factor or time specific factor, whether they are playing a role. In other words, if there is a problem of heterogeneity, whether it is individual heterogeneity or time heterogeneity, whether that affects the dependent variable wage. Because here's the thing, the fact that you are not collecting a variable over time may affect the results. The fact that there is a time also can affect the result. Now remember, the pooled OLS does not respect time. So you are saying that, okay, you don't respect time, but what if time is affecting something? So that's what you want to test. Okay. And we did that here. And this is the results that you get. The same thing. Okay. So you can see that the p-value is 0. Okay. And if the p-value is 0, we can now reject the null hypothesis and indicate that there is a significant time effect or individual effect. In short, individuals' heterogeneity, like the fact that there's heterogeneity in the individuals, there's a lot of heterogeneity. That can affect your wage. That can affect your wage. That's all it's saying. And also the fact that we are dealing with that 8-time period, the fact that there is a time dimension can also affect the wage of an individual. So that is a conclusion. So you reject the null hypothesis in favor of the alternative, which actually indicates that there is an effect, and the effect is significant. So do not ignore. So with that, if the effect is significant, it means that you cannot use pooled OLS. That's what it means. You can't. So you got to go ahead and rather you go and use either fixed effect model or a random effect model, which is the next thing we are going to check. So we come to the fixed effect or the random effect. Which one should we use? Now, there is a method for determining whether the model is fixed effect model or is a random effect model. The test is called the Hausman specification test. Sometimes it is called Durbin-Wu-Hausman specification test. Please, anytime you are writing a journal, try and quote the test statistic, which I have here. I'll come back to that. But the null hypothesis is that both the random effect and the fixed effect estimators are consistent, but then the random effect is more efficient. Okay. And because the random effect is more efficient, it's always good to use the Durbin-Wu test to support that. If the Durbin-Wu test supports the random effect, you use a random effect. But if the Durbin-Wu test or Hausman test doesn't support a random effect, then you don't use a random effect, which means you're going to use a fixed effect. So what is a test? This is a test. The Hausman test is H equal to the beta estimate from the random effect, the difference between the beta estimate from the random effect and the beta estimate from the fixed effect. The transpose of that, okay, multiplying the variance of these two. So you are looking at the expected value of these two, okay, the transpose of that, and the reciprocal of the variance of these two. All of these become like the test statistic. And this is distributed as a chi-square distribution. Okay. So you do this, normally you just write it, but remember that the R will give you the answer straight away. Now, so you are checking for the differences between the random effects, the differences in the variance of the random effect versus that of the fixed effect, and the difference in the variance covariance vectors. Okay. If it is not positive, then there's another test you can use, which is called Moore-Penrose generalized inverse test. That one is also a chi-square distributed test. And if the Hausman test is not significant, which means that the p-value is greater than 5%, that is when you use a random effect. If it is significant, which means the p-value is less than 5%, then you use the fixed effect. Now, I put a clause here that the Hausman test is also used when you choose between OLS and the two-stage least squares. So let's say you want to check whether we should use OLS or we should use two-stage. You can use the Hausman test to guide you. See, the way you write a Hausman test is similar. Oh, by the way, two-stage least squares is one of the things I planned I would have done. It is something we do when we are dealing with instrumental variables, okay? Especially when there is endogeneity or there's a belief that there is endogeneity, and then you want to correct the endogeneity. It's one way you use to correct the endogeneity. Okay. So let's go and do the Hausman test. Remember that in the Hausman analysis, random effect assumes that the unobserved individual factors are not correlated with the error term. In fact, we know this already from the random effect model, that any of the independent variables have no dependency with the errors. Why in this case, the errors is the individual effect, not the time, not the noise. Okay, remember here, there are always three errors: the time specific factor, the individual specific factor, and then the noise. So we're going to do that. If the p-value is significant, like we have said, you use a fixed effect. If the p-value is not, you use a random effect. Another way of writing the null hypothesis is that the individual specific factor, the UI, is not correlated with this. If that is the case, the null is actually saying that the random effect is suitable. Now watch it. If the p-value is less than 5%, we know that we always reject the null, which means you are rejecting random. And then you go for the alternative, which means the alternative is also the fixed effect, as you can see. So let's run the Hausman test. Which model should we go for? The Hausman test is given by pH test. The WRE is the random effect model. The WFE is a fixed effect model. Let's go into the thing and run it. It's here. It's command number 637. So who can tell me the result? Based on this, which one should we use?
The p-value is significant. With significant, we shall use a fixed effect.
That's it. That's it. Okay. So clearly, you can see that a fixed effect is a way to go. Now, you can also test for random effect and the pooled OLS. You see, already, what we just did indicates that the fixed effect is the way to go. So it's not a random effect. So even though I can test for random effect versus pooled OLS, I don't want to test it because already I've rejected the random effect. And if you guys can remember, we've also rejected the pooled OLS. Do you remember?
Yes.
Yeah.
So this test is not a big deal. However, you can go ahead and look at it. Okay, so you're comparing the two. This is an LM test. If it is significant, then we choose the random effect. In fact, it is here. I've done that test here. So this is a pooled OLS. This is a random effect. It is significant. It is significant in both ways. So we can now go ahead and say that there are two of them that you can use, but it doesn't matter whichever. Okay. So this test clearly shows that we should go for the random effect. But even though we should go for the random effect, we still need to test for the fixed effect versus random effect, which we have already done. And then the fixed effect is the win. Okay. All right. So we go to the last one, which is now comparing the fixed effect versus the pooled OLS. Which one do you think it will go for? Based on all this, if we go for fixed effect versus pooled OLS, which one do you think we'll go for?
Doc, the fixed effect.
Why?
Because the test for it showed that using that fixed effect was the best way. As in, when we checked, it was significant. That was the
but that test was comparing the fixed versus random effect. But what I'm showing here is the fixed versus the pooled OLS.
Okay, so Doc, the first one we did showed that the pooled OLS was not, we shouldn't be used.
Yeah, but that one, we were comparing pooled OLS with what?
So we compared pooled with random.
Good. And then we chose which one?
And then we chose random.
Exactly. So that's where the premise is coming from. The premise is that the random was chosen over the pooled. And then the fixed was chosen over the random.
Random.
So obviously the fixed will be chosen over the pooled.
Exactly.
So that's it's a sort of circularity analysis that I'm doing. That's it. All right. So we now know that we are going to finally choose our pooled, that fixed effect. Let's combine all the models we have run together. But this is a result, and you can see that again, it will reject the pooled OLS. To do the final results, you have to install a package called Stargazer. This Stargazer will produce a beautiful table for you so that you don't need to copy too many things into Excel and reorganize it and change all of them. The table is enough. So first you need to invoke the Stargazer, and hopefully it will work when you run the Stargazer. I'm running it. There you go. The test has shown a beautiful, 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 beautiful. It's looking good. I don't know if you guys can see, but let me just go up. See, now you have all of them nicely organized. Do you see that?
Yes.
Sometimes you see your models that you run, and then you see general papers, and you see that they have organized them model 1, model 2, model 3, and things like that. But that's what you are seeing here.
Document time, after it prints like this, you now retype it in Word or you copy and paste.
I know what you're going to say. You're going to wonder whether you still go to Word and all of that. So there's a way you can, let me see what I see here. There's a way you can send all of them into Word. There is a way.
Okay.
But for now, as it is, let me see. You can also export. Let me see whether I can just take it like this. And then just create a certain Word document and see. You see, if it is not so long, it would have been organized automatically. So let's say that if this thing is already in this view, it's currently in a portrait view, but if we decide to put it in landscape view, how do you put that? I just want to put it in landscape view.
So design.
Okay. I show you design.
No, no.
Let's check it.
You have to work through the
Because I have my Zoom showing.
layout. I'm sure it's layout.
Okay, I think so. Good.
Your orientation. Yeah,
That's it. Okay, let's see whether that will show clear. Yeah, a bit of it is hiding, but it's okay. Yeah, but at least it gives an idea. So you can see that the way it is, when you copy and paste, it's all automatically showing the thing according to. So sometimes you have to now do a bit of adjustment. So for example, when I click here and move the tab, so when you click here and move the tab a little, see the way it is moving. Okay, the rest will move along with it. Now remember that the reason why these first ones are not showing is because they are part of those ones that were not available. But at least you should be able to understand what I mean. So in this column, you have the pooled OLS. Then you have the first difference. Then you have the fixed effect. Okay. All of these are panel data models. Then you have the random effects. I could have used RE. Then you have the fixed effect based on time, fixed effect based on two-way. Then you have the robust fixed effect, and then the robust newer west. Okay. When you move this thing backward like that, okay, it can then put each model. The models have got names. It can put each model under each thing like this. Yeah. I hope you guys can sense something. So now you're able to see the models like this. And on the far left, you see the education, experience square, everything, okay, the time dummies, everything. Now, looking at the very bottom, you see that the total number of observations are there for some of them. Those that excluded, some of the observations will be there. The R square is given in all levels. The F statistic is given in all levels. And then finally, the significant values is also given at all levels. So this is just to let you know how the tables can be done. But hey, if you want to go manually and do all of it, that's also up to you. And I can see that, God, we want to do that.
Oh, not at all.
Yes. Okay. As we were running these models, we were already selecting which one. So the rest will be to talk about the significant values. And then one by one, you indicate which model is the best for you. That is how you generate the fixed and the random. This is a final work. But I took this one in a previous one I've done, and it can see that this very one is well organized.
Yes.
And it was from the same R that I did, so it's well organized. Now, question. How do you compare the models? How do you compare the models? Well, first look at the coefficients of each independent variable. Education, Black or Hispanic, I mean, that's ethnicity. All of these are similar. If you check it, they are similar for the pooled OLS and for the random effect. So these coefficients are the same. The pooled OLS standard error, we know that that one, it underestimates the true standard errors because they ignore autocorrelations. Okay. And so normally they are not even supposed to be reported, but they are only reported for comparison. If you check marriage and union premiums, so that is marriage, okay, and union. If you check these ones very carefully, there's a comment on them that they fall below the random effect estimation. In the random effect estimation. So watch the random effect here. Okay. And then check those two. So when you look at union, you see union is 0.106. I don't know if you see it.
Yes, 0.106.
0.106. Okay. Now, check that same union in the pooled OLS. You see that it is 182. So you can see
Yes.
that almost the 11% falls below the 18%.
Yes.
And then when you check marriage as well, marriage is also 11% here, but when you go to the random effect, it's 6% more or less.
Yes.
So the point we are saying is that all of them fall. Okay. When you remove the unobserved effect entirely from the fixed effect, you can see here. So this is one, the fixed effect, the unobserved, like experience and education, are removed. And in all of these different types of fixed effects, they are removed. So when you check that carefully, you will see that the marriage premium falls to 4.7%. So you can see that. So let's check the marriage premium. So you can see that in the last three, it is 4.7%, 4.7%. But when you look at the pooled OLS, it was 11%. Even at the random effect, it was 6%. By the time you get to the fixed effect, it's gone down.
Yes.
So what are you sensing here? You are sensing that the pooled OLS was overestimating the results. Because remember, at the end of the day, which one did we choose? We chose the last three, or the fixed effect.
The fixed, yes.
You know, so the other ones were overestimated. So what it means is that a married person is supposed to earn almost 11% more than an unmarried person. But This was not true. You're supposed to earn more, but not 11% more. It was just about 5% more. When you look at the fixed effect model. Does that make sense?
Yes.
Yeah. So the pooled OLS was a bit deceptive in this context. So you just talk about what you observe.
Okay.
What you observe. Yeah, that's it. Now we go further to when you drop in the marriage premium. Okay. As you can see, the drop in that marriage premium, because it was 11%, is now 5%. That agrees with the idea that men who are more able, and by able, we are talking about, they have higher unobserved effect. Able men are more likely to be married. When we say able men here, what do we mean? Able men are more likely to be married. You see, the word was random effect was higher. Do you remember?
I don't know if
It was 6.4%. So random, the man is not, the man is, the person is not stable. If you are not stable person as a man, the idea is that then you are not stable. Massa, you have money, but you are not what? Stable. Or even if you have money, you are not stable. You are misusing the money, or you are not stable. I'm sure you understand the idea of stability. So, and that was in the random effect. But when it comes to the fixed effect, that means you are stable, you are fixed. Okay? And because you are fixed, then you are more likely to be married than if not. That's the idea. So you are making practical sense of that. That's why in the pooled OLS, a large part of the marriage premium shows the fact that men who are married will earn more, even if they were not married. Okay. Now, it also speaks a lot about the fixed effect, that the 4.7% has at least two possible explanations. Okay. Marriage, you see, and we are talking about only marriage coefficient here. You can do the same thing with the others, provided you are talking about which variable you are interested in. Which variable is driving your hypothesis. Marriage really makes men more productive. That's the first one. Okay. Or employers pay married men a premium because marriage is a signal of stability. That's it. Of course, we know this already from the pooled OLS, but we are even saying this for even the fixed effect. Okay. The other one is a union premium. So if you look at the fixed effect, look at the union. For the union, this time focuses on the fixed effect. You can see that is 8%. 8%, yes. Almost. Not the 18% in the pooled OLS, but 8%. Yeah. So it says that it is about 10 percentage points lower than the OLS one. And you can see the OLS one was 18. And the fixed effect one is 8. So it's about 10% lower. What does this strongly suggest regarding the correlation between union and the unobserved effect? It can tell you something. So watch it. The point is that you're just looking at these numbers and making practical meanings about each one of them. So you should think along. That's the whole thing. We are not interested in it, but you should think along a lot of the things that you see. The fact that you have estimated fixed effect does not mean that you have fully solved all problems. So it's always good to test for autocorrelation and heteroscedasticity. Panel data which violates the axiom that X and Y are independently identically distributed because of time, they will always cause autocorrelation and heteroscedasticity. So you have to check whether there is that issue, serial correlation in there. Now, how do you handle serial correlation? By adjusting the standard errors. Okay. If there's a lot of autocorrelation, Even if you use heteroscedastic robust standard errors, it will not be consistent. Whatever one will have there, even if it's newer West standard errors, it will not be consistent. So you got to test for the autocorrelation after you've estimated the fixed effect. And the test is the Bridge-Hagan test, BG test. And this is how you test it. So this is my fixed effect that I already have. We are going with that, but let's check whether there is a problem.
Doc, sorry, a question.
Yeah, go ahead.
So initially we were on how to compare the models. And we started with, we compare the coefficients. And now here we are on test of serial correlation. Is that a continuation?
Oh, yes. Now, how you compare the models here, we finished.
Okay.
I had to even pick a few of them and talk around them. And I also asked a question in the end here that you should pick on, because this is not a paper you are writing. But if whatever paper you are writing, you identify key variables that you want to interpret and understand how those key variables mean in the final model.
Okay.
So if you have a final model and you are using fixed effect, okay, everything shows that you have to use fixed effect. Check how the variable you are interested in differ if it was not fixed effect you are looking at. Does that make sense?
Okay.
Yeah.
Yes.
So look for things, look for anomalies, look for changes, look for differences, look for variabilities in the data. Don't just report the results and stay there. Think through.
Okay.
Yeah. And now that aside, we've selected the fixed effect. Now we are saying that even the fixed effect will suffer from autocorrelation. So check to see whether it is there. The null hypothesis is always the fact that there is no autocorrelation. The alternative hypothesis says there is autocorrelation. If the p-value is less than 5%, you are rejecting the null of no autocorrelation. Therefore, you are concluding that autocorrelation is there or serial correlation is there, which is a problem. So let's go and see that test. That test is here. Where's that? So this is a Bridge-Hagan test here. And it's down there. You can see that the p-value is 0. The null hypothesis says that there's no serial correlation. Now, we are rejecting it. So what are we concluding? Alternative. It means that serial correlation is there. So that idiosyncratic error has serial correlation. So you see that even fixed effect will have it, isn't it?
Yes.
So how do you handle it? Use something we call clustered standard errors, aka heteroscedastic autocorrelated consistent standard errors. We've mentioned it before. We've mentioned it before. Now, those standard errors, they assume that no correlation between the errors of different groups. Okay? So there's no correlation. So even if you are this and I am that, and you belong to foreign bank and I belong to domestic bank, the fact that we belong to different groups does not mean that there is any correlation. So we belong to different groups means that there is no correlation between us. That is the assumption it makes. But it allows for heteroscedasticity across the groups. So there is no constant variance across the group. The groups will differ, but you and I will not differ. The groups will differ, but you and I will not differ. So you have to calculate new standard errors here and use it to run the p-values again. The standard errors that are calculated, that new standard error is called Arellano method standard errors. And then you estimate that. Let's go and see how you do that. So that one is in this command here. You use the 2 packages of sandwich and LM test, then you run that result. This is it. So you can see that here, we have corrected for the standard errors, and you can see that almost everything is significant. Yeah. Remember, the focus is just on the p-values because the standard errors are going to change. Nothing else is changing. Remember, this is also on the fixed effect. So other factors will not come in, just the fixed effect model. And remember, the fixed effect has ignored those fixed variables. So you can see that it's a beautiful thing here for most of the independent variables, especially the time dummies are highly corrected in this context. So that is one thing you can check for. And by the way, in our model, we had that. In our result, we had that last column. That corrects for it. You can also test for cross-sectional dependence. You can test for it. What is that? Cross-sectional dependence comes on when the individuals, whether they are companies, when they react to a shock. Okay. So let's say there's a shock in the economy, like COVID. And this shock has affected everybody. Okay. We normally talk about the 1973 OPEC oil, but I'm talking about COVID here because COVID was a big shock. Things like the Arab Spring, financial crisis errors, all of these things are shocks. If these shocks are there, then the estimators can be inefficient and bad inferences can result. So it is very important to check whether there are any shocks that are affecting the thing. Now, these shocks can be tested using two tests. One of them is Bridge-Pagan LM test. The other is Pasaran, cross-sectional dependence test. I'm going to do both of them. In both, the null hypothesis says that there is no cross-sectional dependence. Both of them, the null says that there is no cross-sectional dependence. So you can run that test here. And again, all of these codes are in your slides. So the first one is a Pasaran test. Yeah. Pasaran CD test. And the second one is that. So if you look at the Pasaran CD test, the p-value is 0. The second one too, the p-value is 0. So you reject the null. What was the null? The null says that there is no cross-sectional dependencies. So you are rejecting that null, which means that there is cross-sectional dependence. Okay. So you've been able to dictate that there is cross. So these tests are tests, you should bring them in your table if you did. So how do you correct for it? How do you correct for all of these cross-sectional dependencies? Well, apart from that cross-sectional dependence, there could even be other things. So let's look at those other things before we correct all of them together. Panel heteroscedasticity, contemporaneous correlation of the errors, cross-sectional dependency that we spoke about, serially correlated errors. All of them, we can correct them using something called panel corrected standard error, PCS. So let's run that. Okay. Panel corrected standard error. So watch it. We are not doing anything now. We are just having a different model and correcting for the standard errors. So we do that here. And this panel corrected standard error is by a group, two guys called Beck and Katz. So I ran that. Watch it. Okay. It has given us significant results, but it's supposed to have corrected for the cross-sectional dependence as well. By, sometimes some people call it Beck and Katz panel corrected standard errors. Okay, solved. And you can see that it's solved. It's solved. Now the question is, so the whole thing is, have you made sure that you handled everything? That's the whole point. Now, Beck and Katz suggested that you should estimate the model, okay, and by OLS, and they propose a sandwich of the various covariance methods, which we have just said is the panel corrected standard errors. What it does is that it will give you the robust nature of the work. It is robust. In other words, it stands against heteroscedasticity. It stands against cross-sectional dependency. Okay? It is very, very robust against contemporaneous correlation, or what you might call serial correlation. It will stand against all of it. So Beck and Katz panel corrected standard errors is magical. But Driscoll and Cray provides an easy extension to estimate not just the panel corrected standard error, but the robust newer West standard errors in panel regression. Panel regression that have cross-sectional dependencies, like we have. But this one will be robust to both autocorrelation and serial correlation and cross-sectional dependencies. It is like the mother of all. Maybe it will not do anything. Okay, maybe it will not do anything, but let's run that. So we've indicated that these guys suggested an estimator that is robust to heteroscedasticity, robust to autocorrelation by correcting the standard errors, robust to spatial and temporal dependence, which means it also includes cross-sectional dependence. And sometimes it is called SCC, okay, SCC. They are all good when the sample size is large. You can run that as well. Like I said, all of these things that you're running, some of them will not do anything. So I just ran that to look at it. It also gives the same thing as the previous one did. It gives the same thing. So at least, the whole thing is that you are arguing that you've been able to do all. Now that we've done all of it, let's put everything together now. Okay, we've done everything. Let's put everything together. And this, okay. I think that some of the things must be rate tied. So I need to go and then look at this thing. Let me just tell you. If you go and check these things well, you may see the mistake because they are supposed to follow a certain order. Okay. So watch it. The first one is a pooled OLS. That pooled OLS must match this first one here. Okay. So pooled OLS is pooled OLS. The second one is a first difference, and that is a first difference. The third one is fixed effect. Okay. That is a fixed effect. The next one is random effect. That is a random effect here. The next one is fixed effect two-way. That is a TWFE here. Then random effect or robust fixed effect.
Okay.
So that is a robust fixed effect. Then W newer West fixed effect. That is robust newer West fixed effect. Then followed by let's see, this is where I think, okay, you have fixed effect with hack. That is fixed effect with hack. Fixed effect with panel correction. That is what we call the Beck and Cars. Fixed effect with hack. Then comma, we have fixed effect with SCC. That is a Driscoll and Cray. And then, to be honest, it looks like everything is in order. Maybe this thing is so big, that's how I'm sensing.
As suspected.
It's so big that the table cannot show all. So because the table cannot show all, what I can do quickly, just to prove that maybe that's the case, is I can run the whole thing again here, remove the first, let's say 1, 2, 3, 4, 5, 6. I'm just removing the first 6, which is before the newer West. So I'm going to do the same thing here. 1, 2, 3, 4, 6. Hopefully. Hopefully I've done the right thing. Yeah, that's it. There you go. So the table is so big, that's why it's not showing. So when I cut them off, you can see it. Now it's looking like a good, sensible table. So the robust newer West is there, the FE hack is there, the Beck and Driscoll and Cray. All of them are showing beautiful, beautiful, lessons here. Now I know that they will not show the other bits at the bottom because those ones are usually following the original. Let me just bring the pooled OLS. Okay. In fact, let me just bring you know what? Let me just bring the pooled OLS, the fixed effect and the random effect. So the pooled OLS, I just want to do the RE, that is a random effect. And then I want to do the SE, FE, that's a fixed effect. I want to remove the first difference. So again, I'll bring the pooled OLS here, comma. You bring the fixed effect and then the random effect. So this is a random effect. And now let's do the fixed effect, this one. Hopefully it works. I think it will work. Okay, let me rerun this. Oops. Okay. That's it. Let's see. Yeah, it has worked. So let's show the results. So it's showing the bottom, the observations, the R squared, the F statistics. Okay. So now it has the rest of the tables here. So basically, that is how your stargazer can generate all of the results. As for this, once you send it to your table 1, you can have table 1, table 2, table 3, and then you now talk around them. You talk around them, you talk around, you talk around. What I will do is next week, I'm going to just give you articles that have used some of these things.
Okay.
To help you know how to interpret them. But basically, that is how you conclude with all your work. Well, with this one that I did, this was a concluded table combining everything in here. So finally, which one do you go for? Is it, first thing you got to do when you're doing panel estimations, ask yourself, is it a fixed effect or random event? Use Hobsbawm test, but use theory to justify your point. If it is fixed effect, do a two-way. Okay? But always include robust standard errors. Start with the heteroscedastic autocorrelated robust standard errors, but always try to go further. Use the newer West standard errors, use the Beck and Kaz, use the Driscoll and Cray, and check if there is any cross-sectional dependence. If not, go by the previous hack. If yes, use the panel corrected standard errors or the Driscoll and Cray standard errors. That is how you handle everything. Wow. So use this to be able to now know how you will execute